So at this point, we have just learned the chain rule for finding the derivative of composite functions. And so now we're going to look at a couple examples of using the chain rule. So whenever you first learn a new rule or a new trick or a new method, it's always useful to write out any formulas or any list of steps, have it written out to the side next to you while you're working some examples so that it better ingrains in your brain and you don't get confused. So first thing we're going to do is write out the chain rule. So the chain rule, again, involving composite functions, has to do with it when you have a function f composed with a function g. So f composed g of x, the derivative of the composite function is going to equal the derivative of the outer function, which we've called f, with respect to g of x, times the derivative of g with respect to x. Okay. And so once you identify what your g and your f is, this is usually fairly straightforward, and it's just a matter of using the formula. The tricky part is sometimes identifying what is your inner function, what is your outer function. So let's look at an example. Let's say we have a function h of x equal to 3x squared minus 7x to the power of 5. Now, one way you probably know to do this is to write out and expand the 5 binomials, 3x squared minus 7x 5 times, and multiply it all together, simplify that long polynomial, and use the power rule. Multiplying 5 binomials together, though, can take up a lot of time. So, using the chain rule can actually help you get this done quicker, and it'll still give you the correct derivative. So, first thing we're going to do is identify an inner and outer function. You want to note that 3x squared minus 7x is a statement by itself. And then it's being acted upon by another operator, in this case being raised to the power of 5. So one thing you can try is, say, let a variable u equal what you think may be the inner function, 3x squared minus 7x. So then the entire expression h of x would end up equaling u to the 5th. This is actually a good sign you can use the chain rule if you can do this, because if you let a secondary variable equal a complicated expression, and that simplifies down to fully get rid of the original variable, like we've done here, there's no more x's, then that means you can use the chain rule by letting u be that inner function. That's going to be your g of x. And then x to the 5th is going to be your f of x. And if you want to double check yourself, it's quite simple. Write out let f of x equal x to the 5th and g of x equal 3x squared minus 7x. Then calculate f composed g of x. And what do you know? That ends up equaling 3x squared minus 7x to the power of 5, which is exactly what we originally had. So indeed, breaking apart h into two new functions f and g does indeed hold true. We chose the correct f and g. So now let's actually use this in the chain rule. All right, so according to the chain rule, as we've written on the previous page over here, the first thing we need to find is the derivative of f with respect to g of x. So we need f prime of g of x. One of the best ways to do that is to just take the derivative of f and then plug in g of x in place of x. The derivative of f evaluated at g of x. Okay. And the derivative of f is, of course, 5x to the fourth. That's the power rule we learned forever ago. So the derivative of f with respect to g of x is 3x squared minus 7x to the power of 4. Okay, so that's the first part. The other part we need to find is the derivative of g with respect to x. Usually that's a bit simpler because you don't have to plug anything in after the fact. It's already in terms of g. Of course, the derivative of g with respect to x is 6x minus 7, and that's the second part we need. So by the chain rule, which we have learned, the grand derivative of h of x, which we have stated as f composed g of x, derivative of that is equal to 3x squared minus 7x to the power of 4 times 6x minus 7. And there's one example of using the chain rule to find a derivative with less work than just trying to expand algebraically and use the power rule.